Okay, hi everyone. I'm testing a new way of doing a lecture, so let me know what you think. This is lecture 13 on kinetics. So this follows on from our previous lectures on kinematics. Those are kind of funky words, aren't they? Kinematics means the movement of things, and kinetics is more to do with forces and energy. So before we saw how things can move, how you can write relative velocity at one point in terms of another, relative acceleration, and movement in a rotating frame and all that. But really, to make that all useful, you can't just use how things move relative to each other. You need to add how forces now affect all the movements, and that's what this lecture is about. So really, this is about how to use what's called conservation laws, conservation of linear and angular momentum. So let's start simple. Let's consider one particle. So a case that you know, but remember this is a vector version. So we've got a mass, one particle with mass m, that's heading in a velocity v. Its total linear momentum, which sometimes is shown as L, is its mass times its velocity vector. Now this only changes if we apply a force to the mass. If we don't, it will just continue travelling in a straight line, straight along v, happy forever, for the rest of eternity. But if we apply a force, and this is a vector, so this should be underlined here, then the first law we're going to use is that the rate of change of the linear momentum in time is equal to the force. And if you assume the mass doesn't change in time, it does the rocket, for example, but not in our little particle, then this just becomes mass times the acceleration equals force. I'm sure you've all seen that. It's Newton's second law. I'm just kind of rephrasing it again to work you up to the next law now. So we call this conservation of linear momentum. It's the total linear momentum only change of the forces. Okay, now for another one, which I think you've seen as well before. Another principle, you have another conservation if you're talking about rotation. So let's assume you've got this mass, just one little particle, with a velocity v, and a distance r, a vector distance r, from some origin, and let's say it's sort of kind of fixed, like there's a little rope holding this to the origin O, and it starts spinning around and around and around. So if you don't place any force on it, imagine there's no air resistance, nothing, no gravity, it'll just keep rotating around and around forever. So this is another principle of conservation. We say that the angular momentum is conserved. This can be different than Newton's second law. So in vector form, angular momentum, sometimes we show h, it should be underlined because it's also a vector, is the distance, the vector from the origin, cross product, the linear momentum. And this only changes when we apply torque. So let's say, so the way we phrase this is the total change in time, the change in time, rate of change in time of the angular momentum, which equals this here, this is still just the angular momentum. You can rewrite this as, using the product rule, you first differentiate in r, crossed with what's left over, plus r, cross product, differentiate this part. Okay, so we just use the product rule for differentiation. So I've crossed out this term here because r dot, as r is following the particle around, is the same as the particle velocity. So this becomes v crossed with v, and any vector crossed with itself is always 0. So the result of this, the result of the change of angular momentum is just r, and this should be underlined, sorry, crossed m, v dot underlined. So, okay. And this only changes when we apply torque, and you write torque as to equals the vector from the origin crossed with an applied force. So just to rewrite that again, the angular momentum, rate of change of angular momentum, which is this here, equals the applied torque. And the fact that these two things are equal and that we make them equal is what we call conservation of angular momentum. So this isn't just blah blah theory. This is the thing you need to use. You need to use this equation here, and this should be underlined here and here too, I'm afraid, and Newton's second law, That's how you're going to solve how things move when you apply forces. Those are the two results you need, okay? So you can look at the derivation if you like, but you need to use these results. So we use equations 1 and 3 to solve and find the motion in terms of applied forces. Okay, so that's just for one particle. That's a pretty straightforward case. Right, so now let's move on to the case of this course, a rigid body. So in this case, things are turned into integrals rather than particles, but we're not going to focus too much on knowing how to do that. First, the most useful thing to do, well, here's our rigid body to begin with. And it's really useful to use the center of mass of this body, which I've denoted by this point G. And the vector that takes you from whatever origin we have, and you can choose what the origin is, but whatever origin is from O to G, we're going to use that vector as rho G. I'm going to use rho G because rho is kind of like mass density thing, and it reminds us that it's the vector of the center of mass. And the way we define that is that the total mass times this vector rho G is the integral of every position in the rigid body. So this is the vector from O to some position in the rigid body times that element of mass of that at that position. So an element of mass can be rewritten in terms of the actual mass density times dx dy, which is a little area if you're in 2D. If you're in 3D, you have to adjust this and so on and so forth. Okay, so that's the definition of the center of mass. So now we can write that the change in linear momentum is the derivative in time of the integral of the total momentum, which is the velocity vector, this should be underlined, times a little element of mass. But this is pretty much, you can show that for rigid bodies that this is identical to the velocity of the center of mass. Obviously here we're assuming that the mass doesn't change, and we are assuming that there's a rigid body, because when you move an integral, when you move a derivative in and out of an integral, you do need to make some assumptions, but let's not worry about that. So now the statement of linear momentum is that the total change in linear momentum has to equal whatever forces we apply to the rigid body. So here I've written out some forces as an example. We've got force F1 here in the corner, and these are vectors. We've got a force vector F2 here. So the total change in linear momentum is the sum of all the forces. And there can be more than two, which is why we write a big sum here, n meaning over each of these forces, F1, F2, F3, F4. Okay, conservation of linear. Now, that's conservation of linear momentum. I don't know why it's written angular momentum there. That's maybe it means to say I'm moving on to conservation of angular momentum now. So moving on to conservation of angular momentum. So just leave the screen like that. This case now, the total change in angular momentum is an integral over the change of angular momentum of each element in the body. So that's vector r to the element times the element's crossed by the element's acceleration times a little part of its mass. And what we're going to do is it's much easier to rewrite this in terms of the center of mass. So I'm going to come over here to rewrite this in terms of the center of mass. A little bit ugly, this picture, but I'll try and explain my way through it. So for each vector r, we're going to rewrite it in terms of the center of mass plus a vector which goes from the center of mass to that point in the body. So if you can see here, from the origin to the center of mass, then to the point. Okay? And one of the reasons that's very useful is that if you integrate both sides of this equation, right? So if this equation is true for every r and every rg, this is a g here, you can integrate in both sides of the equation. So the integral on the left becomes this, the integral on the right becomes these two sums here. But this thing here on the left is just the definition of the center of mass. If you integrate the center of mass over every element in the body, because the vector of the center of mass doesn't depend on the position, you can take that outside the integral. Once you take it outside the integral of all the elements of mass just becomes a total mass. So this integral here turns into just the vector of the center of mass times the total mass. And this one here, well, I don't know what to do with this one. But in any case, as you can see, the same term appears on the left and the right, so you can cancel them, and you find that the integral over this vectors here, which point from the center of mass to an element in the body, is 0. So that's why it's really useful to rewrite things in terms of this. Okay, so moving up back to our the rate of change of angular momentum, we've got these vectors r that point to any position in the body. We can rewrite each of these as a sum from the sum to the center of mass plus a vector from the center of mass. So substitute these in here. And now I'm just going to distribute this, because the cross product is linear. We can just distribute this and rewrite this whole thing here in terms of 4 integrals. The first integral is the Rg term crossed with the Rg dot, which I've put here. And this is we usually identify with the moment of inertia times alpha. Then the second integral, I'm just going to get rho g crossed with rho g double dot, and I'm going to put it here. The third integral, I'm going to get Rg crossed with rho g double dot and put it here. And the last one is rho g crossed with Rg double dot. Now, okay, that's quite long. Don't worry too much about it. But this term here, all in the big box, for a rigid body is 0. So all you're left with is the first integral is the moment of inertia around the center of mass times the angular acceleration of the body around its center of mass, plus this thing here, which again, rho g, these vectors rho g don't depend on the position in the body, so you can move this whole thing outside the integral, and you're left with an integral of each of the elements of mass, so that just becomes the total mass, and then you're just left with rho g crossed with rho g double dot total mass. So a nice simple expression. So if you like derivations, have a look at this, but what we need to use actually is just this result here. So I'm just going to move on to show you more about how to use this. So if you do like derivations, I'm just going to quickly discuss, just point out why this is 0. You might be thinking, why is this 0? Well, here you go. The first term is 0 because you can rewrite this like so. What I've done is I've taken out of the integral the cross with a rho g double dot because it doesn't depend on on these positions in the body. So this thing by definition is 0, as we just saw above, because if you're using an origin that is the center of mass, then these vectors integrated everywhere become 0. A similar story happens for the next integral, but to show that we need to do some manipulation. First, at the acceleration of every point like this in the body, if it's a rigid body, can be written like so, where omega dot is alpha actually, so maybe I should have just used alpha. So this you saw from our previous lectures from using a reference that's a rotating reference. So now I'm going to substitute this into the integral which I said is 0. So how does that work? First, you can take our rho g out of the integral because it doesn't depend on the position in the body, so that's what I've done here. And then here I just substituted this part above, and that's why you get 2 integrals here. You get one integral with this term here, and you can remove omega dot or alpha because it also doesn't depend on the position of the body, and then you get just an integral of Rg again, and that's 0 because again we've shown that that's 0. And again the same thing happens with the other term. Okay? So that explains why the end result, when you're using the origin, when you're using your origin as your center of mass, you get a nice simple expression. But here, remember, the vector rho g can have a different origin. It can be pointing from anywhere. Okay. So just to summarize, now we've just figured out that the rate of change of angular momentum can be written in this nice compact way, and now the state conservation of angular momentum, it says that this equals the torque, or in other words that the angular momentum only changes when you apply torque. So I've just rewritten this below. Torque, by definition, now I've used the sum to say lots of forces, is Rn, the position to where the force is. So let's go to the diagram here on the left. R1 is the position it goes from the origin to the point of where the force is. the force F1 is, and R2 is from the origin to the point of where the force F2 is, and that's how you calculate the total torque around O. So note that this is the torque around O, okay? So this is when you have the origin O anywhere you like. So I'd like to make a note here that what happens if we used O as G? What if we placed our origin at G? Well, rho G in this case would be 0. So if you're just looking at the rate of change, the conservation of angular momentum of a body around its center of mass, rho G would be 0, and you just have an easier expression that the moment of inertia times its angular acceleration equals the torque. Okay? So we use equations 1 and 2, so 1 being the conservation of linear momentum, or sort of Newton's second law, and 2 to determine how a rigid body moves due to applied forces. Okay? That's the most important thing you need to take out of this. You're going to use these equations. It's nice to derive it, because then you understand enough about it to use it really and kind of remember who these vectors are. Okay? So I've got an example for you. I think, yeah, I've got an example for you. Should I give that in a separate video? I think I'll do that in a separate video.